Hello there, and welcome to the Night Science Facts channel. Tonight, we'll be taking a very slow, very gentle journey into one of the most extraordinary and mysterious phenomena in all of the known universe: black holes. These quiet giants of the cosmos have captivated scientists, philosophers, and dreamers alike for well over a century. And tonight, in the calm and stillness of wherever you are right now, we're going to explore them together. Not with urgency or tension, but with the same quiet wonder you might feel watching the stars on a clear night from somewhere very peaceful and very still. There's something uniquely soothing about the universe when you slow down long enough to truly look at it. Black holes, despite their dramatic name, are in so many ways places of profound stillness. They sit at the hearts of galaxies. They wait in the deep silence between stars. They hold time itself in their gravitational embrace. And tonight, we're going to visit them, fact by gentle fact, as the hours grow soft around you. Before we begin, I'd like to invite you to settle in a little more deeply. If you're lying down, let your body sink gently into whatever surface is beneath you. Let your shoulders fall. Let your jaw unclench. Let your hands rest open at your sides or folded softly across your chest. Take one slow breath in through your nose. Hold it just a moment and let it out through your mouth, slowly, like a long, quiet exhale into the night. You don't need to remember everything you hear tonight. You don't need to take notes or stay alert. Just let the words wash over you, the way starlight washes over the surface of a still lake. You can simply listen. The universe is very old and very patient, and tonight it has nothing but time for you. Let's begin. For most of human history, we didn't have a name for black holes. The concept existed in mathematical theory long before the phrase itself was ever spoken aloud. It wasn't until 1967 that the physicist John Archibald Wheeler, during a lecture in New York, used the term black hole in the way we use it today. Before that, scientists referred to these objects using much colder, more technical language. Phrases like gravitationally completely collapsed objects or frozen stars. Wheeler's simple two-word phrase caught on almost immediately, spreading through the scientific community and eventually into popular culture. It's remarkable to think that one of the most iconic phrases in all of modern science is, in the grand sweep of cosmic time, only a handful of decades old. And yet, the objects it describes have existed for billions upon billions of years, quietly and patiently, long before any human ever thought to name them. Long before Einstein, long before modern physics, a quiet English clergyman named John Michell sat down in the late 1700s and did something extraordinary. In 1783, Michell wrote a paper in which he proposed the existence of what he called dark stars. Objects so massive and so dense that their gravitational pull would prevent even light from escaping. He arrived at this idea simply by applying Newtonian mechanics, reasoning that if gravity could slow things down, then a sufficiently massive body might slow light itself to a standstill. His ideas were largely forgotten for over a century, lost in the flow of scientific history. It's a quiet, slightly melancholy footnote. A man thinking carefully and correctly about the universe in a time when the tools to verify his thinking didn't yet exist. The universe kept his secret for him, patiently, until the world was ready to listen. In 1915, Albert Einstein published his general theory of relativity, a sweeping reimagining of gravity as the curvature of space and time, rather than a simple invisible force. His equations described the universe with extraordinary precision. But buried within those equations was a strange solution, one that described a point in space so densely curved that nothing could escape it. Einstein himself was deeply uncomfortable with this result. He believed it must be a mathematical artifact, an anomaly, not a real thing. He published a paper in 1939 specifically arguing that such objects could not actually form in nature. The universe, it turns out, did not share his hesitation. Black holes are real, abundant, and scattered throughout the cosmos, in numbers that would likely have surprised him deeply. There's something almost charming about the idea. The greatest physicist in history, slightly unsettled by his own equations. In the winter of 1915, just weeks after Einstein published his general relativity equations, a German physicist named Karl Schwarzschild found the first exact solution to those equations. He did this not in a quiet university office, but from the Eastern Front during the First World War, where he was serving as an artillery officer. He mailed his solution to Einstein from the trenches. Einstein wrote back, genuinely impressed, saying he had not expected the problem to be solved so exactly, so quickly. Schwarzschild's solution described what we now call the Schwarzschild radius, the size to which an object must be compressed before it becomes a black hole. Schwarzschild died just months later from an illness contracted during the war. He never knew what his solution would eventually mean for our understanding of the universe. There is something deeply moving about that. A man standing in the cold and mud of a war, quietly solving one of the deepest puzzles in physics. Despite the name, a black hole is not an empty space. It is not a void or a gap or an absence of something. A black hole is, in fact, an incredibly dense concentration of matter. Mass compressed so tightly into so small a space that the fabric of space-time around it curves completely back upon itself. The whole part of the name refers to the fact that nothing, not even light, can escape once it crosses the boundary. But inside that boundary, there is something, an enormous amount of mass, compressed to an almost incomprehensibly small point called a singularity. It's a subtle but beautiful distinction. Black holes aren't nothingness. They're more like the opposite, an almost unimaginable concentration of something wrapped in the quietest darkness in the universe. The boundary surrounding a black hole, the point of no return beyond which nothing can escape, is called the event horizon. This name comes from the idea that events occurring beyond that boundary cannot send any signal to the outside universe. They are, in a sense, invisible to us, beyond the horizon of what we can ever observe or know. The event horizon isn't a physical surface. You can't touch it or stand on it. It's more like a threshold, an invisible line drawn in space where the rules of the universe quietly change. If you were to approach a black hole, you would not see the event horizon. You would not feel it until, depending on the size of the black hole, it might already be too late. It is perhaps the most profound invisible boundary in all of nature, a line where the knowable ends and the unknowable begins. Not all event horizons are the same size. For a black hole with the mass of our Sun, if the Sun were somehow compressed into a black hole, the event horizon would be only about 3 kilometers across. But for the supermassive black holes that sit at the centers of large galaxies, the event horizon can be almost incomprehensibly vast. The black hole at the center of the galaxy, M87, famously photographed in 2019, has an event horizon with a diameter of roughly 38 billion kilometers. That is larger than our entire solar system. The distance from the Sun to Neptune, the outermost planet in our solar system, is about 4.5 billion kilometers. The event horizon of M87's central black hole is more than 8 times that size. It sits at the heart of its galaxy like a great dark ocean, silent and ancient beyond measure. One of the most quietly extraordinary things about black holes is what they do to time. According to Einstein's general theory of relativity, gravity doesn't just bend space, it bends time as well. The stronger the gravitational field, the more slowly time passes. Near the event horizon of a black hole, gravity is so intense that time slows almost to a stop. If you were watching a friend fall toward a black hole from a safe distance, you would see them appear to slow down as they approached the event horizon, their movements becoming more and more sluggish, their image growing redder and dimmer. From your friend's perspective, nothing unusual would happen. Time, from their point of view, would flow normally. They would cross the event horizon without noticing any particular threshold. But from yours, they would seem to freeze, caught forever at the edge of the black hole, like a photograph. Time is not fixed. It is soft and flexible, and black holes reveal that more clearly than anything else in the universe. Before we return to more soothing territory, let's acknowledge one of the stranger, though in a scientific sense, fascinating phenomena associated with black holes. If you were to fall into a small, stellar mass black hole, the gravitational difference between your head and your feet would be so extreme that you would be stretched out lengthwise, like taffy, in a process physicists have whimsically named spaghettification. The part of your body closest to the black hole would experience enormously stronger gravity than the part farthest away, and this tidal difference would pull you apart in a long, thin stream. It sounds alarming, but it is purely a function of scale. For a supermassive black hole, the tidal forces at the event horizon would be far gentler. So gentle, in fact, that you could cross the event horizon of M87's central black hole without any physical discomfort whatsoever. The universe has a way of softening its edges at the largest scales. Not all black holes are the same. Scientists currently recognize at least 3 broad categories. Stellar mass black holes form when massive stars collapse at the end of their lives, and they typically have masses between about 5 and several tens of times the mass of our Sun. Intermediate mass black holes, which are less well understood, fall somewhere in the middle, with masses ranging from hundreds to tens of thousands of solar masses. And then there are supermassive black holes, the quiet titans at the hearts of most large galaxies, with masses ranging from millions to many billions of times the mass of our Sun. There may also be a 4th category, primordial black holes, potentially formed in the very early universe, though these remain theoretical. The universe, it seems, does not do things in just one size. Right at the center of our home galaxy, the Milky Way, there sits a supermassive black hole known as Sagittarius A star, written with an asterisk and pronounced Sagittarius A star. Its mass is approximately 4 million times the mass of our Sun. It sits about 26,000 light-years from Earth, which sounds enormously distant, and in human terms, it absolutely is. But on cosmic scales, it is essentially our nearest galactic neighbor of this kind. Astronomers have been tracking stars orbiting Sagittarius, a star, for decades, watching them trace tight elliptical paths around an invisible center, pulled by gravity so intense that nothing else could explain the motion. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius, a star, revealing a glowing ring of hot gas surrounding a dark central shadow. It was, in many ways, like seeing the heartbeat of our own galaxy for the very first time. On April 10th, 2019, an image was shared with the world that many scientists had spent their entire careers working toward. It showed a bright, slightly asymmetric ring of orange and golden light surrounding a dark circular shadow, the first direct image ever captured of a black hole and its surrounding region. The black hole in question was the supermassive one at the center of the galaxy M87, located about 55 million light-years from Earth. The image was captured by the Event Horizon Telescope, not a single telescope, but a global network of radio observatories working in concert, effectively creating an Earth-sized dish. The resolution required to capture this image was roughly equivalent to taking a photograph of a single orange sitting on the surface of the moon. It was one of the most technically extraordinary achievements in the history of observational astronomy, and the result was something quietly, deeply beautiful. The image of M87's black hole didn't come from a single person, or a single team, or even a single country. It was the product of a collaboration involving over 200 scientists from around the world, across dozens of institutions, working for years to coordinate, calibrate, and process the enormous amounts of data collected from 8 radio observatories spread across 4 continents. The data itself was so voluminous, roughly 5 petabytes or 5 million gigabytes, that it could not be sent over the internet. Instead, it was recorded onto hard drives and physically flown to processing centers in the United States and Germany. This vast international effort, quiet and methodical over many years, ultimately produced a single circular image about the size of a thumbnail. Sometimes the most important things in science, and perhaps in life, require patience and the willingness to work together across great distances. Among the many scientists who contributed to the first black hole image, one name became widely known in the days after the announcement. Katie Booman, a computer scientist who, as a graduate student at MIT, helped develop one of the key algorithms used to reconstruct the image from the telescope data. A photograph of her smiling beside a stack of hard drives containing the data became one of the most shared images of 2019. She was quick to credit the entire team, noting repeatedly that the achievement belonged to hundreds of people. But her story reminded the world that the great discoveries of science are often built on the work of young, thoughtful, dedicated people who sit at their computers late into the night, patiently working on a piece of a puzzle they may not live to see completed. There is something very gentle and very human about that. One of the most common misconceptions about black holes is that they actively pull things toward them, that they are like cosmic vacuum cleaners, roaming through space and swallowing everything in their path. In reality, a black hole's gravity behaves just like any other gravitational field. If you replace the sun with a black hole of exactly the same mass, the planets of our solar system would continue orbiting in exactly the same paths they follow today. Nothing would be sucked in. Earth would not be drawn toward the black hole. The only difference would be that the sun's light and heat would be gone. A much more immediate concern, admittedly. Black holes are dangerous only if you get very close to them. At a safe distance, they are simply gravitational objects, like any star or planet, just far more compact and, at their cores, far more intense. In 1974, the physicist Stephen Hawking made one of the most surprising theoretical discoveries in the history of black hole physics. He proposed that black holes are not entirely black, that they actually emit a faint, slow trickle of radiation, now called Hawking radiation, due to quantum mechanical effects near the event horizon. The process is incredibly slow. A stellar mass black hole would take far longer than the current age of the universe to evaporate even slightly. But the idea that black holes slowly lose mass over time, eventually shrinking and disappearing, was revolutionary. It connected two of the great pillars of modern physics, general relativity and quantum mechanics, in a way that had never been done before. Hawking himself reportedly announced the result to a colleague with an enormous grin, saying, "I have discovered something wonderful." It is one of the few things in physics that feels almost like a story with an ending. The universe, over unimaginable stretches of time, quietly tidying up after itself. Despite the theoretical elegance of Hawking's prediction, no one has ever directly detected Hawking radiation from an actual black hole. The reason is simple. For any black hole massive enough for us to know about, the radiation is fantastically faint, orders of magnitude fainter than the cosmic microwave background radiation that fills all of space. It would be, by any practical measure, invisible to any instrument we currently possess. Scientists hope that one day, perhaps with the detection of tiny primordial black holes, if they exist, or through laboratory analogues using acoustic black holes in ultra-cold fluids, the existence of Hawking radiation may be confirmed. Until then, it remains one of the most beautiful and well-supported theoretical predictions in physics that still waits quietly for its moment of direct confirmation. At the center of a black hole lies what physicists call a singularity, a point of infinite density and zero volume, where the known laws of physics simply cease to function. The equations we use to describe space, time, matter, and energy all produce infinities at the singularity, which is a mathematical way of saying we don't know what happens here. Most physicists believe that the singularity is not a real physical thing, but rather a sign that our current theories are incomplete. A future theory of quantum gravity, one that seamlessly merges general relativity and quantum mechanics, would likely replace the singularity with something more physically meaningful. In this sense, the center of a black hole is not just a place of darkness, but a place of open questions, a doorway into the unknown that the universe has left open, waiting for us to understand it better. Not all black holes are simple, static spheres of gravity. Many black holes rotate, sometimes extraordinarily fast. A spinning black hole is described by what physicists call the Kerr solution, named after the New Zealand mathematician Roy Kerr, who worked it out in 1963. A rotating black hole drags the fabric of space-time around with it in a process called frame dragging, like a spoon stirring thick honey, pulling the surrounding space into its rotation. The region of space being dragged in this way is called the ergosphere, and it lies just outside the event horizon. Interestingly, within the ergosphere, it is theoretically possible to extract energy from the black hole through a process called the Penrose process, essentially stealing energy from the rotation itself. A black hole can spin so fast that its event horizon approaches a maximum theoretical rate. Some black holes observed in nature appear to be spinning at close to this maximum speed. The environments surrounding actively feeding black holes can generate magnetic fields of extraordinary intensity. These fields arise from the swirling ionized gas, called a plasma, that forms a flattened disk around the black hole as matter falls inward. The magnetic fields become tangled and compressed as the gas spirals inward, growing enormously strong. In some cases, these magnetic fields play a key role in launching the powerful jets of material that shoot outward from the poles of certain black holes. These jets can extend for millions of light years, streaming energy and matter deep into the surrounding galaxy and beyond. The magnetic fields themselves can be so powerful near certain neutron stars and black hole systems that they would strip the iron from your blood at a distance of 1,000 kilometers. The universe is full of forces that dwarf anything we encounter in daily life, and yet they coexist somehow with the quiet stillness of a late night and a blanket and the sound of a calm voice in the dark. Before John Wheeler popularized the term black hole in 1967, physicists who studied these objects often called them frozen stars. The name came from the way a distant observer would perceive an object falling toward the event horizon. Because of gravitational time dilation, the infalling object would appear to slow down and freeze, its image becoming redder and more faded over time, but never quite disappearing. It would look, to the outside observer, as though the collapsing star had simply paused, frozen at the moment of its most extreme compression. The name frozen star is in many ways poetically accurate, but it doesn't quite capture the full strangeness and wonder of what these objects truly are. Black hole, with its suggestion of infinite darkness and irresistible depth, perhaps comes closer, not because it is scientifically precise, but because it carries, in just 2 words, a kind of cosmic weight. One of the remarkable things about black holes is that even though they cannot be seen directly, their masses can be measured with great precision using the effects of their gravity. Astronomers observe the motions of stars and gas clouds orbiting the black hole, measure their velocities, and use the laws of gravity to calculate the mass of the invisible central object. This is the same principle by which we weigh the planets in our solar system, by watching how other things orbit around them. In the case of Sagittarius A star, astronomers have spent decades tracking the orbits of individual stars near the galactic center. Some of these stars have orbital periods of only a few years, racing around an invisible point at thousands of kilometers per second. Their orbits, traced with patience and precision over many years of observation, spell out the mass of the black hole as clearly as letters on a page. The Milky Way is a large galaxy containing an estimated 200 to 400 billion stars. Many of the most massive stars that have lived and died in its long history would have ended their lives in stellar collapse, leaving behind black holes. Current estimates suggest that our galaxy may contain somewhere between 10 million and 1 billion stellar mass black holes, most of them silent and dark, detectable only if they happen to be actively pulling matter from a companion star. The vast majority of black holes in the Milky Way are invisible to us, sitting quietly in the dark between the stars, holding their gravitational peace. We are embedded in a galaxy that is, in a sense, full of them, scattered throughout the spiral arms like seeds in a field, patient and unseen. When two black holes orbit each other closely enough, they will gradually spiral toward one another, losing energy in the form of gravitational waves, ripples in the fabric of space-time, until they finally collide and merge into a single, larger black hole. This merger event is one of the most energetic processes in the known universe. In the fraction of a second during which two black holes merge, they can release more energy in gravitational waves than all the stars in the observable universe emit in light during that same instant. The resulting black hole rings and vibrates, ringing down in physicists' language, as it settles into its new shape, sending out one final fading series of gravitational waves. The whole event is extraordinarily violent by any human scale of reference. And yet, it produces no light, no sound, no fireworks visible to the naked eye. Just a quiet ripple in the invisible fabric of reality, spreading outward at the speed of light. On September 14th, 2015, instruments at the LIGO Observatory, the Laser Interferometer Gravitational Wave Observatory, detected a faint signal that had travelled 1.3 billion light-years across the universe. It lasted less than a second, but in that brief chirp of data, it carried the unmistakable signature of two black holes, one about 36 times the mass of the Sun, and another about 29 times, spiraling together and merging into a single object. This was the first direct detection of gravitational waves, something Einstein had predicted in 1916, but believed would never be measurable. The discovery earned 3 of the LIGO scientists the Nobel Prize in Physics in 2017, and it opened an entirely new way of listening to the universe, not through light or radio waves, but through the soft vibrations of space-time itself, like feeling the bass note of a cosmic song, too deep and too vast for any instrument but the most sensitive ones we have ever built. To give some sense of the extraordinary sensitivity required to detect gravitational waves, the LIGO detectors measure changes in the lengths of their 4-kilometer-long arms. The signal from the merging black holes in 2015 caused a change in the length of those arms of approximately 1/10,000th the diameter of a proton. A proton is already incomprehensibly small, far smaller than any atom. 1/10,000th of that. And yet, LIGO detected it. Human beings built instruments sensitive enough to measure a distortion in space-time smaller than the smallest known particles of matter. It is difficult to hold this fact in the mind without feeling something, a kind of quiet wonder at the patience and ingenuity of science, and perhaps also a kind of humility in the face of a universe that hides its deepest truths in disturbances of almost unimaginable smallness. There is a famous phrase in black hole physics: black holes have no hair. This principle, developed in the 1960s and 70s, states that a black hole can be completely described by just 3 properties: its mass, its spin, and its electric charge. Nothing else. No matter what you throw into a black hole, a book, a star, a teapot, a living person, all information about the specific nature of that object is lost. All that survives, encoded in the black hole's properties, is the total mass, the total angular momentum, and the total charge. Everything else is hair, and black holes have none. This principle has profound implications and has led to one of the deepest ongoing debates in theoretical physics, the black hole information paradox, which asks what truly happens to the information about the things that fall into a black hole. Does it vanish forever, or is it somehow preserved? The universe, so far, has not answered. The black hole information paradox was first clearly articulated by Stephen Hawking in the mid-1970s. If black holes emit Hawking radiation and eventually evaporate, and if that radiation carries no information about what fell in, then the information about all the matter and energy that ever crossed the event horizon would simply vanish. But quantum mechanics insists that information cannot be destroyed. It can be transformed, hidden, scattered, but never truly eliminated. Reconciling this with Hawking's evaporation result has been one of the most persistent puzzles in theoretical physics for over 40 years. Hawking himself changed his position on the issue multiple times over the course of his life. The latest approaches suggest that information is somehow encoded in the correlations within Hawking radiation, subtly, invisibly, but not completely lost. The universe keeps its records. We just haven't learned to read them yet. When a black hole is actively feeding, pulling in large amounts of gas and dust from its surroundings, the material forms a superheated, rapidly rotating disk of plasma called an accretion disk. As matter falls through this disk toward the event horizon, gravitational energy is converted into heat and light with extraordinary efficiency. An actively accreting supermassive black hole can emit more light and energy than all the hundreds of billions of stars in the surrounding galaxy combined. These objects are called quasars, from quasi-stellar objects, and they are among the most luminous things in the observable universe. Some quasars, observed at great distances, are so bright that they were originally mistaken for stars. They are not stars. They are the flaming accretion disks of supermassive black holes, burning bright across billions of light years. The universe, it turns out, contains fires of a kind we had barely imagined. The first quasars were discovered in the early 1960s by radio astronomers who noticed that certain point-like sources of radio emission corresponded to faint blue objects when examined optically. What puzzled scientists was that these objects, once their spectra were measured, turned out to be enormously distant, and thus enormously luminous. To shine so brightly from such extraordinary distances, they had to be releasing energy at a rate that no known stellar process could explain. It took years of theoretical work and observational progress before the scientific community converged on the explanation we accept today. Quasars are powered by supermassive black holes in the centers of distant early galaxies, caught in a period of intense and voracious accretion. What had seemed like unremarkable radio sources turned out to be among the most energetic phenomena in the history of the cosmos. Science has a wonderful habit of doing that, turning the unremarkable into the astonishing. As far as astronomers can tell, almost every large galaxy in the observable universe contains a supermassive black hole at its center. This is not a small claim. It means that hundreds of billions of galaxies, each containing hundreds of billions of stars, are each, at their quiet cores, home to an object of unimaginable mass and gravitational power. Our own Milky Way, Andromeda, Messier 87, the Sombrero Galaxy, Centaurus A, all harbor supermassive black holes. The relationship between a galaxy and its central black hole appears to be deeply intertwined. The mass of a galaxy's central black hole is correlated with the mass of the galaxy's central bulge, even though the black hole is many orders of magnitude smaller. How and why this relationship exists is still being actively studied, but it suggests that black holes and galaxies grow up together, that the lives of the very largest and the very heaviest are, in ways we are still learning to trace, quietly connected. The largest black holes known to science are found at the centers of certain massive elliptical galaxies. TON 618, a quasar located about 10.4 billion light-years from Earth, contains a black hole with a mass of approximately 66 billion solar masses, 66 billion times the mass of our Sun. If you placed this black hole at the center of our solar system, its event horizon would extend past the orbit of Neptune. Its Schwarzschild radius, the radius of its event horizon, is about 195 billion kilometers. Numbers like this resist easy comprehension. They sit beyond the reach of intuition, somewhere in the space between number and abstraction. All we can do is sit quietly with them and let them remind us how vast, how ancient, and how generous the universe is with its wonders. The universe is approximately 13.8 billion years old, and yet some of the quasars we observe, objects powered by supermassive black holes, are seen at distances corresponding to when the universe was less than 1 billion years old. This means that black holes of extraordinary size had already formed within the first 10% of the universe's existence. How this happened is one of the great open questions of modern cosmology. Black holes of that size, in that shorter time, could not easily have grown from simple stellar collapse. Some models suggest that in the early universe, massive direct collapse black holes formed from enormous clouds of primordial gas, bypassing the stellar stage entirely. Others propose that early black holes merged rapidly and repeatedly. The early universe, it seems, was busier and more productive than we once imagined, growing its giants early in the first quiet chapters of cosmic history, while most matter approaching a black hole does so in the form of gas and dust. Some black holes, particularly those at the dense centers of galaxies, are surrounded by large numbers of stars, orbiting at relatively close range. These stellar populations trace the gravitational influence of the central black hole through their motions, helping astronomers map the black hole's mass and its reach. Near the center of the Milky Way, a cluster of young massive stars, called the S-stars, orbit Sagittarius, a star at remarkable speeds and on dramatically elliptical paths. The fastest of these, a star called S2, completes an orbit in just about 16 years and reaches speeds of nearly 3% of the speed of light at its closest approach to the black hole. Watching these stars trace their ancient paths around an invisible center, year after year, is one of the most eloquent demonstrations of gravitational physics in the observable universe. Some black holes, particularly those that are actively accreting matter, launch narrow, highly focused streams of particles and energy from their polar regions, extending for thousands or even millions of light-years into surrounding space. These jets, moving at close to the speed of light, are among the most energetic sustained phenomena in the universe. The exact mechanism by which they form is still an area of active research, but it is believed to involve the interaction between the black hole's spin, the magnetic fields threading the accretion disk, and the intense plasma of the disk itself. In the case of M87, the famous black hole whose image was captured in 2019, the jet was first observed by astronomer Heber Curtis in 1918, more than a century ago, long before anyone understood what it was or where it came from. That jet is still there, still streaming silently across the cosmos, as it has been for longer than our entire recorded human history. The jets launched by supermassive black holes are not merely local phenomena. They can deposit enormous amounts of energy into the space surrounding a galaxy, heating gas, suppressing star formation, and shaping the large-scale structure of the galaxy over millions of years. This process, known as AGN feedback, after active galactic nucleus, is now understood to be one of the key mechanisms by which the growth of galaxies is regulated over cosmic time. Without this feedback, models suggest that galaxies would continue forming stars unchecked, growing far larger than they actually are. In a very real sense, the black holes at the hearts of galaxies are not passive occupants. They are active participants in the life of the galaxy, breathing out energy that shapes the space around them across distances of millions of light years. There is something almost ecological about this, a deep and intricate feedback loop between the very smallest and very largest scales. When the Event Horizon Telescope captured the image of M87's central black hole in 2019, what it actually imaged was not the event horizon directly, but the shadow of the black hole, the dark region at the center of the glowing ring of emission. This shadow is actually larger than the event horizon itself, because the black hole's gravity bends the paths of light rays traveling near it. Light that passes close to the event horizon, but doesn't fall in, gets bent around it, and some of it gets captured in unstable circular orbits at a region called the photon sphere, located 1.5 times the Schwarzschild radius from the center. The shadow, as seen by a distant observer, appears to be about 2.5 times the size of the event horizon. This enlarging effect, a consequence of gravitational lensing, means that black holes appear slightly larger to us than they geometrically are. Even in their dimensions, they gently stretch and distort our assumptions about space. For many years, astronomers knew of two broad categories of black holes: stellar mass, a few to a few tens of solar masses, and supermassive, millions to billions of solar masses. But in between lay a gap: the intermediate mass black holes, ranging from roughly 100 to 100,000 solar masses. Evidence for these objects has been building slowly and quietly over the years, emerging from observations of dense star clusters, peculiar X-ray sources, and gravitational wave signals that don't quite fit the stellar mass template. In 2020, the LIGO and Virgo collaborations detected gravitational waves from a merger that produced a remnant of about 142 solar masses, placing it firmly in the intermediate mass category. The universe, it appears, does not like empty spaces in its catalogue of wonders. Where a gap exists, something will eventually be found to fill it. Long before the first photograph of a black hole was taken in 2019, black holes had already become one of the most recognizable symbols of cosmic mystery in popular culture. They appeared in novels, films, and television shows, from the 1979 Disney film The Black Hole to Christopher Nolan's 2014 film Interstellar, for which physicist Kip Thorne, one of the founders of LIGO, served as a scientific consultant. The black hole Gargantua depicted in Interstellar was rendered using a physically accurate simulation of the effects of a rapidly spinning black hole on the light around it. And, the rendering produced unexpected results that the visual effects team had not anticipated, leading to a real scientific publication. Sometimes art and science move together, each illuminating the other in ways that neither would have achieved alone. When a massive star reaches the end of its life and its core collapses, the outcome depends on how massive the collapsing core is. If the core mass falls below a certain threshold, the collapse is halted by the repulsive force between neutrons, quantum mechanical pressure that resists further compression. And the result is a neutron star, an incredibly dense ball of neutrons, typically about 20 kilometers in diameter, with a mass of about 1 to 2 suns. If the core mass exceeds this threshold, however, nothing can halt the collapse, and a black hole forms instead. Neutron stars and black holes are thus related, siblings in the family of stellar remnants, born from the same kind of event, differentiated only by mass. Neutron stars are extraordinary in their own right. Some spin hundreds of times per second, their surfaces crackling with magnetic fields 1 trillion times stronger than Earth's. They are, in a sense, the universe's near misses. Objects that came so close to becoming black holes, but held on by just the narrowest margin. To help appreciate just how extreme the densities involved in these collapsed objects are, a teaspoon of neutron star material, about 5 milliliters, would weigh approximately 1 billion metric tons on Earth. That's roughly equal to the weight of all the water in Lake Erie. This density is close to the density of an atomic nucleus, meaning that in a neutron star, matter has been compressed to the point where the space between atoms no longer exists. All the empty space that ordinarily fills atoms has been squeezed out, and what remains is a kind of vast atomic-scale crystal of neutrons rotating in space. A black hole is denser still, or rather, its density is not meaningfully defined in the usual sense. All its mass is compressed to a singularity of 0 size. These are materials, in a philosophical sense, that transcend the ordinary categories of matter. The first stellar mass black hole ever identified with confidence was Cygnus X1, an X-ray binary system located about 6,000 light-years from Earth in the constellation Cygnus. It was detected as a strong X-ray source in 1964 during one of the earliest rocket-borne X-ray astronomy surveys. By 1972, analysis of the system's orbital dynamics had led many astronomers to conclude that the compact object in the system, which was pulling mass off a companion blue supergiant star, had a mass too great to be a neutron star. The invisible object was almost certainly a black hole. Cygnus X1 has the distinction of being the subject of a famous friendly wager between Stephen Hawking and Kip Thorne. Hawking bet in 1974 that it was not a black hole, as a form of insurance against his own theoretical work. By 1990, he conceded the bet. Kip Thorne received a subscription to the adult magazine Penthouse. The universe, occasionally, has a sense of humor. Hawking's theoretical prediction was not just that black holes emit radiation. It was that they emit radiation in a very specific, mathematically precise pattern. Black holes radiate as perfect black bodies. Their emission spectrum is exactly the same as that of an idealized object that absorbs all incoming radiation and emits thermal radiation purely as a function of its temperature. This makes black holes one of the most perfectly realized physical idealizations in all of nature. Real objects, stars, heated metals, light bulbs, only approximate blackbody behavior. Black holes, according to Hawking's calculation, achieve it exactly. The temperature of this radiation is inversely proportional to the black hole's mass. Smaller black holes are hotter, larger ones are cooler. The Hawking temperature of Sagittarius. A star, our galaxy's central black hole, is approximately 1.5 times 10 to the minus 14 degrees above absolute zero, more than 1 trillion times colder than the cosmic microwave background. It is the faintest whisper of warmth imaginable. Sagittarius. A star is, at present, one of the quieter supermassive black holes we know of. It accretes very little matter. The gas available to it at the galactic center is sparse and poorly organized, and it emits only modest amounts of energy compared to the blazing quasars seen in other galaxies. Occasionally, it produces small flares, brief brightenings that last a few hours and may correspond to brief episodes of enhanced accretion or magnetic reconnection events near the event horizon. But these are gentle events, as these things go. In the distant past, Sagittarius A star may have been far more active. Some models suggest that, as recently as 3 to 4 million years ago, around the time our hominid ancestors were walking the African savanna, it may have been significantly more luminous, perhaps even producing a quasar-like episode. The light from that long-ago activity might still be illuminating distant gas clouds, visible in certain radio wavelengths. Even the past is still in some places arriving. In the early 1970s, physicists Jacob Bekenstein and Stephen Hawking developed a set of laws describing the behavior of black holes, and found, to their delight and fascination, that these laws were essentially identical in form to the classical laws of thermodynamics. The area of a black hole's event horizon plays the role of entropy. It can never decrease, mirroring the second law. The surface gravity of a black hole plays the role of temperature, and so on, through all 4 thermodynamic laws. What began as a mathematical analogy has since come to be understood by many physicists as a deep and literal connection. The suggestion that black holes are genuinely thermodynamic objects, that the thermodynamic behavior of matter and energy and information are not separate domains, but aspects of one underlying reality. Bekenstein, who first noticed the parallel, faced significant skepticism initially. Hawking himself was initially dismissive of the idea. The universe, in its patient way, waited for them to catch up. Jacob Bekenstein's proposal that the entropy of a black hole is proportional to the area of its event horizon has implications far beyond black hole physics. It led, eventually, to the development of the holographic principle, the idea that all the information needed to describe a 3-dimensional region of space can be encoded on a 2-dimensional surface bounding that region. In the context of black holes, this means that all the information about everything that has ever fallen into the black hole, every particle, every star, every ancient gas cloud, is somehow encoded on the event horizon, like a vast and unimaginably complex 2-dimensional map. The universe, in this view, might at some fundamental level be less like a 3-dimensional space and more like a hologram, rich and deep in experience, but ultimately encoded on a surface. These are ideas at the very frontier of human understanding, where physics becomes something close to poetry. The most common way a stellar black hole is born begins with a massive star, one considerably larger than our Sun, typically at least about 20 to 25 times as massive. Throughout its life, this star generates energy by fusing lighter elements into heavier ones in its core. Hydrogen into helium, helium into carbon, carbon into oxygen, and so on up the periodic table. Each stage of fusion produces less energy than the last and proceeds more quickly. When the star's core has been converted entirely to iron, the heaviest element that can be produced by fusion without absorbing energy, fusion stops. The core, no longer supported by the outward pressure of nuclear burning, collapses in a fraction of a second. The outer layers fall inward and then bounce outward in a catastrophic explosion, a supernova, while the core, if it is heavy enough, continues to collapse past the neutron star stage and becomes a black hole. It all happens very fast. The entire collapse takes less time than it takes you to draw one breath. The explosion that accompanies the formation of a black hole or a neutron star can briefly outshine an entire galaxy. A supernova at its peak can emit as much light in a single day as the sun will emit over its entire 10 billion year lifetime. Supernovae observed in nearby galaxies can be seen in daylight with the naked eye. The most famous historical naked eye supernova, visible from the northern hemisphere, was observed in 1054 AD by Chinese astronomers and left behind the Crab Nebula, a beautiful, still expanding cloud of gas and a central neutron star that spins 30 times per second. The light from that explosion travelled 6,500 light-years to reach the eyes of observers on Earth. Somewhere in that quiet journey through space, it passed uncountable stars, vast clouds of interstellar gas, the gravitational pull of other worlds, and finally arrived here, on this small planet, to be seen and recorded and remembered. Not every massive star that collapses produces a brilliant supernova. In some cases, when the collapsing core is heavy enough and the collapse rapid enough, the star may simply vanish without a visible explosion. This is called a failed supernova or a direct collapse black hole. Astronomers have been monitoring millions of massive stars in nearby galaxies for signs of this phenomenon, and in at least one case, a massive star in the galaxy NGC 6946, designated N6946-BH1. A star that briefly brightened in 2009 has since disappeared from observations. The most likely explanation is that it collapsed directly into a black hole without a supernova. This is, from a certain perspective, one of the most quietly dramatic things in nature. A star the size of hundreds of millions of our suns, simply blinking out. There one day, gone the next. Nothing remaining but a dark point in space, and a small absence where light used to be. And now we reach the quiet midpoint of our journey tonight. 50 facts behind us, 50 more still to come. The universe outside these words is as dark and vast as it always was. The stars are still burning. Sagittarius. A star is still sitting quietly at the center of our galaxy, turning its slow and ancient gravity outward into the arms of the Milky Way. And you are still here, resting and listening, perhaps already drifting a little towards sleep. Take a slow breath here if you like. Let your body relax a little more deeply. Let the muscles in your face soften. Let the space behind your eyes go quiet. We're going to continue now, gently, into the second half of our journey. There are still so many remarkable things to discover. In the very early universe, within the first fraction of a second after the Big Bang, density fluctuations in the extremely hot and dense primordial plasma may have been large enough to cause some regions to collapse directly into black holes. These hypothetical objects are called primordial black holes, and they could have a very wide range of masses, from tiny fractions of a gram to millions of solar masses, depending on when during the early universe they formed. Primordial black holes are particularly interesting because they could, in principle, be dark matter candidates, the mysterious missing mass that makes up roughly 27% of the universe's energy content, but has never been directly detected. If primordial black holes of certain mass ranges exist in large numbers, they could account for some or all of the dark matter. The search for them is ongoing, using gravitational lensing surveys and gravitational wave detectors. The early universe may have left us gifts that we are still learning to find. The nature of dark matter is one of the deepest unsolved problems in modern physics. For decades, the leading candidates have been exotic subatomic particles that interact only very weakly with ordinary matter. WIMPs, axions, sterile neutrinos. But despite enormous efforts using underground detectors, particle accelerators, and astronomical observations, none of these particles has been definitively detected. This has led some physicists to revisit older ideas, including the possibility that dark matter consists entirely or partly of primordial black holes. The universe may have seeded itself in its earliest moments with a population of these objects that now drifts through galaxies invisibly, bending light and tugging at stars through gravity alone, never interacting with anything else, never emitting a single photon, dark and quiet and ancient. The universe is very good at keeping secrets. Much of what we know about the early universe comes not from direct observation of objects, but from the cosmic microwave background, CMB, a faint glow of microwave radiation that fills the entire sky uniformly in all directions. This radiation is the afterglow of the Big Bang, the relic heat from the time about 380,000 years after the beginning, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing light to travel freely for the first time. The CMB carries within its tiny temperature variations, fluctuations of just a few hundred thousandths of a degree, an imprint of the density variations of the early universe. It is, in a sense, a photograph of the universe as it looked 13.8 billion years ago. Studying it tells us about the formation of large-scale structure, the composition of the universe, and possibly the conditions under which primordial black holes might have formed. When people visualize the effect of a black hole on space, they often imagine the two-dimensional analogy of a bowling ball placed on a rubber sheet. The sheet curves downward toward the ball, and nearby marbles roll toward it. This is a useful illustration, but it only shows curvature in 2 dimensions. In reality, a black hole curves space in all 3 spatial dimensions simultaneously, in every direction outward from its center, equally. Space curves toward it from above, below, left, right, forward, backward. There is no direction from which you could approach a black hole and not be pulled toward it. This 3-dimensional curvature of space is what gives the black hole its perfectly spherical event horizon in the case of a non-rotating black hole. Gravity, in Einstein's framework, is not a force pulling objects together. It is the curvature of space-time itself, and everything that moves through that space follows the curves, the way water follows the contours of a landscape. At a distance of approximately 1.5 times the Schwarzschild radius from the center of a non-rotating black hole lies the photon sphere, a region where gravity is strong enough that light can travel in circular orbits. A photon, moving at exactly the right angle and speed in this region, would, in principle, orbit the black hole indefinitely, never falling in and never escaping. In practice, these orbits are unstable. Any slight perturbation will send the photon either inward to be captured or outward to escape. But the photon sphere has observable consequences. It creates a characteristic bright ring visible around the black hole in images like the one captured by the Event Horizon Telescope. Light that passes near but outside the photon sphere gets bent dramatically, wrapping around the black hole 1, 2, or even multiple times before escaping. Multiple images of background objects appear stacked concentrically around the dark shadow, a visual signature of extreme gravity written in light. Because a black hole bends the paths of light rays passing near it, it can act as a gravitational lens, distorting, brightening, and multiplying the images of background objects. A distant galaxy directly behind a black hole would appear as a bright ring called an Einstein ring, its image smeared symmetrically around the black hole in a complete circle. If slightly offset, the galaxy's image might appear as 2 or more separate arcs. These effects are not merely theoretical curiosities. They are observed regularly and are used by astronomers to study both the black holes doing the lensing and the background objects being lensed. Gravitational microlensing, a subtler version of the same effect produced by objects too small or too distant to resolve individually, is one of the tools used to search for dark matter and to detect black holes that don't happen to be accreting material. The universe uses its gravity as a kind of cosmic optics, bending and focusing light in ways that reveal things otherwise hidden. The gas in the inner regions of an accretion disk, the closest matter to the event horizon, reaches extraordinary temperatures. As it spirals inward through the intense gravitational field, gravitational potential energy is converted into kinetic and thermal energy. In the very innermost regions of the disk, temperatures can reach hundreds of millions, or even billions, of degrees Kelvin. At these temperatures, the gas emits not just visible light, but X-rays and gamma rays, the highest energy forms of electromagnetic radiation. X-ray observatories in space, like NASA's Chandra X-ray Observatory and the European XMM Newton Telescope, observe these hot inner disks and use their emission to study the structure of spacetime very close to the event horizon. The universe, in its extremes, glows with light invisible to human eyes, vast energies being released in the quiet heart of cosmic darkness. Our nearest large galactic neighbor, the Andromeda Galaxy, is currently approaching the Milky Way at approximately 110 kilometers per second. In approximately 4.5 billion years, the two galaxies will collide and merge, eventually forming a single large elliptical galaxy. When they merge, their respective central black holes, Sagittarius, a star and Andromeda's own supermassive black hole, which has a mass of roughly 100 million solar masses, will also eventually find each other, spiral together, and merge. This black hole merger, billions of years from now, will send gravitational waves rippling through the cosmos more powerful than any we have yet detected. The stars of both galaxies will mostly not collide. There is too much empty space between them. But the galaxies will be transformed, rearranged, and eventually settled into a new form. It is a catastrophe on a scale no human language was designed to describe. And it will happen, quietly, billions of years from now, whether anyone is watching or not. When two galaxies merge and their central black holes begin to orbit each other, there is a well-understood mechanism, the gravitational slingshot of surrounding stars, that causes the two black holes to lose energy and spiral closer together. But when they reach a separation of about 1 parsec, roughly 3.26 light-years, this mechanism becomes far less efficient. The black holes lose the ability to fling stars away as readily, and the in-spiral stalls. This is known as the final parsec problem. How the black holes manage to get close enough to begin emitting significant gravitational waves and complete their merger is still not fully resolved. Proposed solutions include the presence of gas that carries away angular momentum, the influence of a third black hole, and triaxial galaxy shapes that keep supplying new stars to be ejected. The universe clearly solves this problem. We observe the results of black hole mergers. But the exact mechanics remain a quiet, open question at the frontier of astrophysics. While LIGO detects gravitational waves from mergers of stellar mass compact objects, another class of detector, pulsar timing arrays, may be on the verge of detecting the low-frequency gravitational wave background produced by the combined signal of supermassive black hole mergers throughout the universe. Pulsars are rapidly rotating neutron stars that emit beams of radio waves with extraordinary clockwork regularity, making them some of the most precise natural clocks in the cosmos. A network of pulsars spread across the galaxy, monitored carefully over decades, is sensitive to the stretching and squeezing of spacetime caused by the gravitational wave background. In 2023, multiple pulsar timing array collaborations around the world announced compelling evidence for just such a background signal, a quiet hum of gravitational waves permeating all of space, produced by the slow spiral and eventual merger of supermassive black hole pairs across the observable universe. We are, it seems, beginning to hear the deep bass note of the cosmos. The mathematics of general relativity, when applied to the Schwarzschild solution, describing a static black hole, contains another type of object, a white hole, which is the exact time reverse of a black hole. While a black hole allows matter and light to enter, but never leave, a white hole would allow matter and light to leave, but never enter. It would spew material outward, unprovoked, from a central singularity, a cosmic fountain rather than a cosmic drain. White holes have no observational evidence to support their existence in nature, and there are good reasons to believe they are not physically realizable. The second law of thermodynamics strongly resists their formation, but they appear naturally and unavoidably in the mathematics of certain black hole spacetime geometries, like symmetrical reflections in a theoretical mirror. The universe, it seems, has room in its equations for things it chooses not to build. One of the most elegant tools in theoretical physics is the Penrose diagram, a type of spacetime diagram developed by mathematician Roger Penrose that represents the entire past and future of a universe in a finite drawing. A Penrose diagram of a static black hole shows not just the black hole itself, but the white hole region, two separate external universes, and the structure of the singularity. All of it mapped, compressed, and made visible on a page. These diagrams reveal features of spacetime geometry that are difficult to see in ordinary representations. For instance, that an eternal black hole, one that has existed for infinite time, is connected by a bridge to another universe, a feature known as an Einstein-Rosen bridge or a wormhole. Whether such structures can actually exist in our universe, and whether they could ever be traversable, are open questions. But Penrose diagrams make the architecture of space-time visible in a way that has no equal. Roger Penrose received the Nobel Prize in Physics in 2020, in part for his work on black holes. A wormhole, also called an Einstein-Rosen bridge, is a hypothetical structure in space-time that connects two separate points, potentially in different regions of space or even different times. They emerge naturally from certain solutions to Einstein's equations. The simplest kind, the Schwarzschild wormhole, is not traversable. It would collapse too quickly for anything to pass through it. Traversable wormholes could, in principle, be kept open by a form of matter or energy with negative energy density, something called exotic matter, which may or may not be physically realizable. Wormholes remain speculative, but they are not idle science fiction. They are genuine solutions to genuine equations, and theoretical physicists take seriously the possibility that they exist somewhere, somehow, in the structure of the universe. The cosmos, patient and full of surprises, has not yet told us everything it contains. One of the most intriguing recent ideas in theoretical physics proposes that Einstein-Rosen bridges, wormholes, are physically equivalent to quantum entanglement between particles. The conjecture, known as ER equals EPR, after Einstein-Rosen and Einstein-Podolsky-Rosen, the two papers describing each phenomenon, was proposed by Juan Maldacena and Leonard Susskind in 2013. It suggests that whenever two particles are quantum entangled, sharing a quantum mechanical connection across any distance, they are, in some sense, connected by a tiny wormhole. The implications of this idea are profound. It suggests a deep and previously unsuspected connection between the geometry of space-time and the quantum correlations between particles. Space itself, in this view, may be woven from the threads of quantum entanglement. Black holes, wormholes, and the quantum connections between particles may all be aspects of a single underlying fabric we are only beginning to discern. In 2012, a group of physicists, Almhiri, Marolf, Polchinski, and Sully, collectively known as AMPS, proposed a thought experiment that created a significant controversy in theoretical physics. If black holes truly preserve information as they evaporate through Hawking radiation, then the radiation emitted later in the black hole's life must be entangled with radiation emitted earlier. But quantum mechanics forbids a particle from being entangled with two different things simultaneously. This creates a contradiction with the smooth, gentle crossing of the event horizon that general relativity predicts. The resolution proposed by AMPS was unsettling. Perhaps the event horizon is not the smooth, uneventful boundary we thought, but is instead a firewall, a region of intense energy that would incinerate anything trying to cross it. The firewall paradox has inspired an enormous outpouring of theoretical work, new ideas, and heated debate. It sits at the intersection of quantum mechanics and general relativity, precisely the place where our understanding is most incomplete and most in need of new ideas. In 1997, Juan Maldacena proposed one of the most far-reaching ideas in modern theoretical physics, the ADS/CFT correspondence, also known as the holographic duality. This conjecture states that a theory of quantum gravity in a certain type of curved spacetime, anti-de Sitter space, is mathematically equivalent to a quantum field theory without gravity on the boundary of that space. Black holes in the ADS interior correspond to specific thermal states in the boundary theory. This correspondence has been used to study enormously complex quantum systems, including quark-gluon plasma, high-temperature superconductors, and quantum fluids, by translating the problem into one involving black holes in curved spacetime, where calculations can be more tractable. It is one of the most fruitful and unexpected bridges in all of physics, connecting black holes, which are objects of astronomical scale, to the behavior of quantum systems at the tiniest scales of matter. The universe, in its deepest structures, seems to reflect itself across scales. Because it is impossible to study actual black holes up close with current technology, physicists have developed what are called analog black holes, laboratory systems that mimic the behavior of black holes in controlled settings. One class of analog uses supersonic fluid flows. When a fluid moves faster than the local speed of sound, a region forms from which sound waves cannot escape, analogous to the event horizon. In 2016, physicist Jeff Steinhauer at the Technion in Israel announced observations of what appeared to be the acoustic equivalent of Hawking radiation in a Bose-Einstein condensate, an ultra-cold quantum fluid flowing faster than the speed of sound. These experiments can't prove that real black holes emit Hawking radiation, but they can test the theoretical framework that predicts it, providing indirect but meaningful support for the idea. The universe's rules are general enough that some of its deepest secrets can be whispered to us by the behavior of cold atoms in a laboratory on Earth. When a star wanders too close to a supermassive black hole, the tidal forces, the difference in gravity between the near side and far side of the star, can become strong enough to overcome the star's own self-gravity and tear it apart. This is called a tidal disruption event. As the star is shredded, roughly half of its mass is ejected into space, while the other half falls back towards the black hole, forming a temporary accretion disk and producing a bright, distinctive flare of radiation that can be detected billions of light years away. Tidal disruption events last for weeks to months, rising and falling in brightness in a characteristic way that allows them to be identified and studied. They provide a rare glimpse of a normally quiescent black hole suddenly waking up, catching a meal briefly before returning to silence. Astronomers have detected hundreds of these events in recent years, each one the record of a star, perhaps with planets, perhaps ancient, quietly ending in a bloom of X-ray light. In some tidal disruption events, the black hole does not merely form a glowing disk. It also launches a narrow relativistic jet of plasma pointed almost directly toward Earth. These events, called jetted tidal disruption events, or sometimes colloquially, the death of a star, can be briefly detectable in gamma rays, X-rays, and radio waves simultaneously, and are among the most energetic events ever observed. The first clearly identified jetted tidal disruption event, detected in 2011 and designated Swift-J 1644+57, released more energy in its jet in a few days than the Sun will radiate in its entire 10 billion year lifetime. It occurred in a galaxy about 3.8 billion light-years away. The signal was still traveling through space when the first multicellular life was appearing on Earth. It arrived here at a moment in time when human beings happened to have the instruments to notice it. The timing of cosmic events and the evolution of intelligence are not coordinated, and yet, sometimes, they meet. Observations of the very early universe reveal quasars, powered by supermassive black holes, at epochs corresponding to redshifts greater than 7, meaning we see them as they were less than 800 million years after the Big Bang. The black holes powering these quasars have masses of billions of solar masses. This is deeply puzzling. A black hole growing continuously at the theoretical maximum rate, the Eddington limit, would take about 800 million years to reach 1 billion solar masses, starting from a seed of 100 solar masses. The timing is just barely possible, and only if growth was nearly continuous and nearly maximal throughout. Many scientists suspect that the seeds of these early black holes were already unusually large, perhaps direct collapse black holes with initial masses of 100,000 solar masses or more. The early universe seems to have been capable of tricks that we are still struggling to explain. It grew its giants faster than we would have guessed, in ways we don't fully understand. Einstein's famous equation, E equals mc squared, tells us that mass and energy are interchangeable, that a small amount of mass corresponds to an enormous amount of energy. Near a black hole, this equivalence becomes dramatically practical. As matter falls through the accretion disk, a significant fraction of its rest mass, the energy equivalent of its mass, is converted into radiation and heat. For comparison, nuclear fusion in the Sun converts about 0.7% of the hydrogen mass into energy. The accretion process around a black hole can convert between 6% and 42% of the infalling mass into energy, depending on the black hole's spin. A maximally spinning black hole, accreting matter through its innermost stable orbit, can achieve a mass-to-energy conversion efficiency of 42%. This makes black hole accretion the most efficient sustained energy conversion process known in the universe, far surpassing nuclear fusion, chemical burning, and anything we have achieved technologically. If we could somehow harness a black hole, we would have an engine of extraordinary power. For now, we simply observe from a very safe and very comfortable distance. The maximum mass of a neutron star before it collapses into a black hole is set by what is called the Tolman-Oppenheimer-Volkoff (TOV) limit. Theoretically, this limit lies somewhere between approximately 2 and 3 solar masses, though its exact value depends on the poorly understood equation of state of neutron star matter, how the pressure of extremely dense neutron matter responds to compression. Observationally, the most massive neutron star firmly identified has a mass of about 2.35 solar masses. Any neutron star more massive than the TOV limit cannot support itself against gravity and must collapse into a black hole. The gravitational wave event, GW 190814, detected in 2019, involved the merger of a black hole with an object of 2.6 solar masses. Whether this object was a very heavy neutron star or a very light black hole remains uncertain, and the debate around it continues to inform our understanding of where the boundary between neutron stars and black holes truly lies. Among the family of neutron stars, a subclass called magnetars deserves special mention. Magnetars possess magnetic fields of extraordinary strength, up to 10 to the 15th power Gauss, roughly a quadrillion times stronger than Earth's magnetic field. They are born when certain massive stars collapse. and their intense magnetic fields drive powerful flares of gamma rays and X-rays. In 2004, a magnata in our galaxy produced a gamma ray flare that briefly compressed the ionosphere of Earth from a distance of 50,000 light-years. The pulse of energy arrived first in gamma rays, then in radio waves, and was so strong that it briefly saturated detectors on multiple space observatories simultaneously. These objects, while not black holes, are intimately related to them. They represent the extreme edge of what a collapsed stellar core can do without quite crossing into the domain of black holes. They are, in a sense, the most extreme objects in the universe that haven't yet become black holes. Around a rotating black hole, just outside the event horizon, lies the ergosphere, a region where space-time is dragged around by the black hole's rotation so strongly that nothing can remain stationary. Everything in the ergosphere, even light, is forced to co-rotate with the black hole. But the ergosphere lies outside the event horizon, which means it is still possible to escape from it. This creates a theoretical possibility known as the Penrose process. An object entering the ergosphere could, in principle, split into two pieces, with one piece falling into the event horizon on a retrograde orbit, and the other escaping with more energy than the original object entered with. The extra energy comes from the rotational energy of the black hole itself, which is slightly reduced each time this process occurs. In the extreme case of a maximally rotating black hole, up to 29% of the black hole's total mass can theoretically be extracted through Penrose processes. A rotating black hole is not just a passive gravitational trap. It is, in principle, an enormous reservoir of stored energy. Given any amount of mass, there is a specific size, the Schwarzschild radius, below which that mass must be compressed in order to form a black hole. For the mass of the Earth, that radius is about 9 millimeters, a marble-sized sphere. For the mass of the Sun, it is about 3 kilometers. For the mass of a mountain, say 10 billion kilograms, the Schwarzschild radius is smaller than an atomic nucleus. This means that in order for ordinary objects to become black holes, they would need to be compressed to extraordinary, practically unachievable densities. Under ordinary conditions of nature, only the collapse of massive stellar cores provides the required combination of mass and compression. The universe is full of mass, but it is sparing with black holes, creating them only under very specific and extreme circumstances. In all the ordinary world we inhabit, black holes are not lurking around corners. They require conditions far beyond anything we will ever encounter in daily life. In 1969, Roger Penrose proposed what is now called the cosmic censorship hypothesis, the idea that all singularities in nature are hidden inside event horizons, that the universe never allows a naked singularity, a singularity visible to the outside world. If naked singularities existed, they would represent points of infinite density from which effects on the outside universe could propagate unpredictably, potentially violating causality and predictability throughout physics. Penrose believed the universe arranges itself to prevent this, always dressing its singularities in event horizons. This hypothesis has never been proven mathematically in full generality, and there are known mathematical solutions that produce naked singularities under very contrived conditions. But in the physical world, all observations are consistent with cosmic censorship holding. The universe, whatever else it may be, appears to keep its deepest secrets behind closed doors. The entropy of a black hole, the measure of the information content, or the number of possible microstates, is given by the Bekenstein-Hawking formula, which is proportional to the area of the event horizon measured in units of the Planck area, the smallest meaningful area in quantum gravity. For a black hole the mass of our Sun, this entropy is approximately 10 to the power of 77 in natural units. The entropy of the actual Sun, by comparison, is about 10 to the power of 57. A black hole contains roughly 10 to the power of 20 times more entropy than the star that formed it. An extraordinary, almost incomprehensible increase in the disorder of the universe. This entropy increase, one of the most dramatic instances of the second law of thermodynamics in action, means that the formation of a black hole is one of the most irreversible processes in nature. Once a star becomes a black hole, the vast majority of the information about its original structure is scrambled, encoded on the event horizon in a form we don't yet know how to read. In August 2017, LIGO and its European partner, Virgo, detected gravitational waves from a different kind of merger. Not two black holes, but two neutron stars colliding. The event, known as GW170817, was remarkable not just for the gravitational wave signal, but because it was simultaneously observed in light across the entire electromagnetic spectrum, from gamma rays to radio waves, and in neutrinos. This was the dawn of what astronomers call multi-messenger astronomy, the ability to observe a single cosmic event through multiple, completely different types of signals. The neutron-star merger was identified as the source of a short gamma-ray burst. Subsequent observations revealed a kilonova, a brilliant explosion produced by the rapid creation of heavy elements through a process called the R process. In a very literal sense, this merger produced gold, platinum, and other heavy elements, scattering them into the universe. Some of the gold in the jewelry people wear was created in events like this, billions of years ago, in distant galaxies. After two black holes merge and form a single remnant, the new black hole is initially distorted. Not a perfect sphere, but lumpy and asymmetric, vibrating like a struck bell. As it settles into its final state, it emits gravitational waves in what is called a ring down, a series of damped oscillations at characteristic frequencies determined by the black hole's mass and spin. These oscillation modes are called quasi-normal modes, and they are a direct fingerprint of the black hole. By measuring the frequencies and damping times of the ring-down signal, physicists can test whether the remnant is indeed a black hole as predicted by general relativity, and not some more exotic compact object. This kind of test, called black hole spectroscopy, is one of the most powerful tools for checking the validity of general relativity in the strong field regime. The universe rings when it changes, and we have learned to listen to those rings. In the very far future of the universe, assuming it continues to expand and cool indefinitely, all stars will have burned out. All neutron stars will have cooled to near absolute zero. All galaxies will have evaporated, their stars flung away by gravitational interactions over inconceivably long timescales. In this cold, dark future universe, the last remaining complex structures will be black holes, and even they will not last forever. By Hawking's calculation, a black hole with the mass of our Sun would take approximately 2 × 10 to the 67th power years to evaporate. a number so large it makes the current age of the universe about 1.4 times 10 to the power of 10 years, look like a vanishingly small fraction of a second. Supermassive black holes would take far, far longer, on the order of 10 to the power of 83 to 10 to the power of 106 years, depending on their mass. But eventually, each one would reach its final moment, a tiny, hot burst of Hawking radiation, and then be gone. The universe would continue in silence, cold, empty, and perhaps, finally, fully at peace. Radio astronomers have spent decades studying the environment near the center of our galaxy, the region surrounding Sagittarius A star, with extraordinary detail. The galactic center is a complex and dynamic place. Hot gas, powerful magnetic fields, young and old stars, supernova remnants, and vast molecular clouds all coexist in the relatively small region within a few hundred light-years of the central black hole. Radio observations reveal long, thin, magnetized filaments stretching perpendicular to the galactic plane, features whose origin is still debated. Dense clusters of young, massive stars sit in orbit around the black hole at distances of a few light-years. This environment is so different from the calm, relatively sparse neighborhood of our Sun, sitting out in one of the spiral arms, far from the galactic center, that it almost feels like a different universe. At the heart of our galaxy, things are decidedly more active, more crowded, and more strange. The center holds its own kind of splendor. Gamma-ray bursts, GRBS, are the most energetic explosions observed in the universe. Brief flashes of gamma radiation that can briefly outshine the rest of the observable universe. They come in two varieties: long GRBs, lasting more than 2 seconds, are thought to be produced when a rapidly rotating massive star collapses to form a black hole, launching a jet of material that punches through the collapsing star and beams intense radiation at the observer. Short GRBs, lasting less than 2 seconds, are produced by the mergers of compact objects, neutron stars, or a neutron star with a black hole. In both cases, a black hole likely forms at the heart of the event. Gamma-ray bursts are cosmic birth announcements of a kind, some of them marking the moments when new black holes are created, lighting up the universe briefly with their formation before returning to darkness. They are detected, on average, about once per day from random directions across the sky. An X-ray binary is a system in which a black hole, or neutron star, orbits a companion star and actively accretes material from it. As material flows from the companion and spirals toward the black hole, it heats up and emits X-rays. These systems are among the best laboratories we have for studying black hole physics in real time. By analyzing the X-ray emission, its spectrum, its variability, its quasi-periodic oscillations, astronomers can infer the mass and spin of the black hole, the structure of the accretion disk, and the behavior of matter in extremely strong gravitational fields. Some X-ray binaries exhibit dramatic outbursts, periods of greatly enhanced accretion, during which the X-ray brightness increases by orders of magnitude in days. These outbursts allow detailed study of how accretion disks form, evolve, and eventually drain. Each one is a natural experiment designed by the universe, running without any intervention from us. And we watch as patiently and attentively as we can, taking notes. One of the reasons black holes are so extraordinary is deeply connected to a foundational fact about the universe: the speed of light, approximately 299,700 92 kilometers per second, is the maximum speed at which any information or material object can travel. This is not merely a technological limitation. It is a fundamental feature of the universe's geometry, built into the very nature of space and time. The reason nothing escapes from inside a black hole's event horizon is not that the black hole is pulling too hard. It is that the escape velocity exceeds the speed of light, and nothing can go faster than light. Even a photon, moving at the maximum possible speed in exactly the right direction, cannot make progress away from the singularity once it is inside the event horizon. Space-time itself, inside the event horizon, is so curved that all possible futures, every possible direction of travel, lead inward. The event horizon is not a wall. It is the shape of space itself, closing off all exits. One of the most disorienting features of a black hole's interior, as described by general relativity, is that once you are inside the event horizon, the direction toward the singularity becomes not a direction in space, but a direction in time. Before crossing the event horizon, you can choose to move toward or away from the black hole, just as you can choose to move left or right. After crossing the event horizon, the singularity is in your future, unavoidably, the same way that tomorrow is unavoidably in your future, no matter what you do today. You cannot choose to move away from it any more than you can choose to move backward in time. This deeply strange geometric property is one of the things that makes the interior of a black hole so conceptually alien. Inside a black hole, the compass of possible futures all point toward the singularity. Time and space trade roles. The ordinary intuitions of everyday life provide no guidance whatsoever. The no-hair theorem, the principle that a black hole is completely characterized by its mass, spin, and charge, has been tested through observations of gravitational wave signals from merging black holes. After a merger, the ring-down signal carries information about the mass and spin of the remnant. If the remnant is indeed a black hole as described by general relativity, its quasi-normal mode frequencies should be determined exactly by these two parameters. Comparing the observed ring-down frequencies with the predictions provides a direct test of the no-hair theorem. Early results from LIGO and Virgo events are consistent with general relativity's predictions, though the signals are not yet precise enough to rule out small deviations. Future, more sensitive detectors, including the planned space-based LISA mission, will provide far more precise measurements, pushing the tests of black hole physics to new levels of accuracy. We are beginning to read the fingerprints of black holes in the vibrations of space-time itself. The Laser Interferometer Space Antenna, LISA, is a planned space-based gravitational wave detector consisting of 3 spacecraft flying in a triangular formation separated by 2.5 million kilometers. This enormous baseline will make LISA sensitive to gravitational waves at much lower frequencies than LIGO, including the waves produced by the inspiral and merger of supermassive black holes, which are too massive to produce the high-frequency signals LIGO can detect. LISA is expected to detect thousands of gravitational wave sources across the universe, including binary stellar mass black holes thousands of years before they merge, neutron star binaries, and the inspirals of small compact objects into supermassive black holes. This last class of events, called extreme mass ratio inspirals, will give us exquisitely precise maps of the space-time geometry around supermassive black holes, providing the most stringent tests of general relativity ever conducted. LISA is scheduled for launch in the mid-2030s. We will have new ears to hear the universe, and we will use them. The division of space into inside and outside the event horizon seems simple, but its implications are profound. From the outside, we can never see what is inside. No information can escape. From the inside, hypothetically, you cannot affect anything outside. No signal can reach the exterior. The two regions are, in a very deep sense, causally disconnected. Yet, they are also spatially continuous. There is no wall, no physical barrier at the event horizon. Someone falling through the event horizon would not, in principle, experience anything unusual at that moment in a large enough black hole. The discontinuity is purely causal, not physical. This blurring of inside and outside into a purely causal distinction has inspired some of the deepest thinking in quantum gravity and the nature of space-time. The universe seems to be telling us that the concepts we use to divide up space in everyday life, walls, surfaces, boundaries, are, at the most fundamental level, something subtler and stranger than they appear. At the heart of black hole physics lies a deep tension between general relativity and quantum mechanics. One manifestation of this tension is the Planck length, approximately 1.6 times 10 to the minus 35 meters, below which the concepts of space and distance as we use them may cease to have physical meaning. This is not merely a practical limitation. It is believed by many physicists to be a fundamental feature of the universe, that space and time are not smooth continua at the smallest scales, but have a granular, discrete structure that emerges at the Planck scale. The singularity at the center of a black hole, in classical general relativity, is a point of zero size, far smaller than the Planck length. This is one of the reasons most physicists believe that general relativity must break down at the singularity, and that a theory of quantum gravity is needed to describe what really happens there. At the Planck scale, we reach the edge of our current knowledge. Beyond it, the universe has not yet fully revealed its nature to us. One of the most remarkable properties of gravitational waves is that they pass through matter almost completely unimpeded. Unlike electromagnetic radiation, which can be absorbed, scattered, and reprocessed by gas, dust, and plasma, gravitational waves simply pass through everything. A gravitational wave produced by a black hole merger, 1 billion light-years away, travels through countless galaxies, star clusters, nebulae, and planetary systems, all the way to our detectors, without being absorbed or significantly scattered. This makes gravitational waves an extraordinarily clean probe of the universe. They carry information about their sources, mass, spin, distance, encoded in their frequency and amplitude, and they deliver that information to us uncontaminated by the intervening medium. In a universe where much of the most interesting physics is hidden behind gas, dust, and opaque plasma, gravitational waves offer a clear, unobstructed view. They are a new sense, a way of touching the universe that light cannot provide. Perhaps no single area of physics has done more to change our understanding of time than the study of black holes and general relativity. Time, in Newton's physics, was absolute, a universal clock ticking at the same rate everywhere in the universe. Einstein showed that this was wrong. Time passes at different rates in different gravitational fields and at different velocities. Black holes push this to the extreme. near the event horizon, time slows almost to a stop relative to a distant observer. At the singularity, insofar as the concept of time has any meaning there, the familiar flow of time may break down entirely. These insights have seeped from theoretical physics into everyday life in subtle ways. GPS satellites, for instance, must account for the relativistic effects of both gravity and velocity on time, or their positional calculations would drift by kilometers per day. Black holes, in this sense, are not just abstract curiosities. They are the most extreme manifestations of a reality that touches everything, everywhere. The accretion disk surrounding an actively feeding black hole is not monochromatic. Different regions glow at different wavelengths determined by temperature, which varies with distance from the black hole. The outermost regions are cooler, emitting infrared and visible light. Moving inward, the temperature rises and the emission shifts to ultraviolet and soft X-rays. The innermost regions, near the event horizon, reach millions to billions of degrees and emit hard X-rays and gamma rays. This multi-wavelength structure allows astronomers using telescopes sensitive to different parts of the spectrum to study different regions of the flow simultaneously. It is as if the black hole writes its story in many languages: infrared, optical, ultraviolet, and X-ray, each telling a chapter of the same tale of matter falling through gravity's deepest well. The center of the Milky Way, home to Sagittarius, a star, is one of the most intensely studied regions of our galaxy, and one of the strangest. Within a few light years of the central black hole, conditions are extreme. The density of stars is millions of times higher than in the solar neighborhood. Gas clouds are heated and ionized by ultraviolet radiation from massive young stars. Magnetic fields are hundreds of times stronger than in the galactic disk. There is a population of very young, massive stars, the S stars, whose orbits bring them breathtakingly close to the black hole, despite the fact that the region near the galactic center should, according to simple models, be inhospitable to star formation. How these young stars came to be there, whether they formed in situ or migrated inward, is one of the puzzles of galactic center research. The universe, as always, refuses to be entirely predictable. In 2012, astronomers announced the discovery of a compact gas cloud, designated G2, on a trajectory taking it very close G2, on a trajectory taking it very close to Sagittarius, a star. There was excitement about what might happen when G2 reached the closest point of its orbit in 2014. Some models predicted the black hole might tidally disrupt the cloud and produce a bright flare, briefly illuminating the galactic center. When the time came, G2 passed relatively close without a dramatic increase in activity, though Sagittarius, a star, showed some heightened variability in the following weeks. Later, analysis suggested that G2 might be a star surrounded by a dusty envelope rather than a pure gas cloud, explaining its resilience against tidal disruption. The event reminded astronomers that even in well-studied environments, the universe continues to surprise, and that the difference between a gas cloud and a star with a dusty cloak can matter enormously to what happens next. When the Event Horizon Telescope captured the image of M87's central black hole, scientists did not merely look at it in wonder, they measured it. The size and shape of the dark shadow at the center of the glowing ring carries information about the mass and spin of the black hole, and about the geometry of the surrounding spacetime. These measurements were compared with the predictions of general relativity for a black hole of the inferred mass. The result? The observations are consistent with general relativity's predictions to within the uncertainties of the measurement. General relativity, first written down in 1915, makes accurate predictions about the shadows of black holes 55 million light-years away. This is extraordinary. It means that the equations Einstein wrote at his desk over 100 years ago describe the geometry of space-time around an object he never believed existed, in a galaxy he could not have imagined observing, with accuracy beyond what he could have dreamed of testing. The universe is not uniformly distributed. Galaxies are gathered into clusters, which are gathered into superclusters, which form the walls and filaments of the cosmic web, an enormous foam-like structure on the largest scales. At the nodes of this web, where filaments intersect, the largest galaxy clusters sit, containing thousands of galaxies. Each large galaxy harbors a supermassive black hole, and the energy output of these black holes, through jets, winds, and radiation, helps shape the evolution of the clusters around them. In the largest galaxy clusters, X-ray observations reveal bubbles in the hot intergalactic gas inflated by jets from the central black hole, enormous cavities, each the size of hundreds of thousands of light-years, pushed out into the surrounding medium. Black holes, though they exist at the smallest scales of the cosmic landscape, shape structure at the very largest. In the universe's architecture, they are quiet, load-bearing pillars, invisible from most angles, but fundamental to the whole structure. If you could somehow hover at a safe distance near a large black hole and look out at the surrounding universe, the night sky would appear profoundly altered. Light from stars and galaxies behind and around the black hole would be bent and redirected by its gravity, appearing in unfamiliar positions and configurations. Stars near the direction of the black hole would appear displaced toward its edges. Stars directly behind the black hole might appear as a ring around it, an Einstein ring. The black hole itself would appear as a dark circular patch in the sky, surrounded by concentric rings of increasingly distorted star images. The entire sky would be warped and rearranged, a funhouse mirror of the real universe, as gravity bended light from every direction. Standing near a black hole, purely hypothetically, you would see the universe from a perspective no human eye has ever seen, a perspective where gravity is the artist and the canvas is the entire sky. The arrow of time, the fact that time appears to flow in only one direction, from past to future, is one of the deepest puzzles in physics. The fundamental laws of physics are, for the most part, symmetric in time. They work equally well forward and backward. And yet, experience tells us unambiguously that time flows one way. The thermodynamic arrow of time, entropy always increases, provides one explanation, but that simply pushes the question back to why entropy was low in the first place. Some physicists, including Roger Penrose, have suggested that the initial low entropy of the universe is connected to the initial conditions of the Big Bang and to the behavior of gravity, particularly the fact that black holes are profoundly low entropy objects when they form but accumulate vast entropy over their lifetimes. The arrow of time in this view is not a coincidence or an illusion, but a consequence of the universe beginning in a very specific, very ordered state. And black holes are part of the machinery by which that order is gradually, irreversibly consumed. For all that we know, and we know a great deal, the science of black holes is still young, still unfinished, still full of open doors. The information paradox remains unresolved. The nature of the singularity is unknown. The quantum behavior of the event horizon is debated. The origin of the largest supermassive black holes is unclear. The mechanism by which some black holes launch jets and others don't is not fully understood. The role of primordial black holes in the cosmos is unknown. Whether wormholes exist, whether naked singularities can form, whether the holographic principle is exactly correct, all of these remain open, and this is not a source of anxiety or frustration. It is a source of extraordinary wonder. Every open question is an invitation. Every unanswered puzzle is a door not yet opened. Black holes sit at the edge of human knowledge, not as a wall, but as a horizon. And beyond every horizon, there is always more. There is a growing sense among theoretical physicists that black holes are not merely one type of exotic object among many, that they may be, in some deep sense, the most fundamental objects in the universe. They appear at the intersection of every major unsolved problem in physics: quantum gravity, the nature of information, the arrow of time, the holographic principle, the structure of space-time itself. Some models of quantum gravity suggest that all particles, at the most fundamental level, can be understood as extremely charged black holes. Others suggest that the entire universe can be understood as a hologram encoded on a two-dimensional surface, with black holes as the key to understanding how three-dimensional reality emerges from this encoding. Whether these ideas are literally true in the way that they are meant, or merely useful analogies, remains to be seen. But the fact that black holes sit at the center of so many of the deepest questions in physics suggests that nature is trying to tell us something important, something patient, something that we are still very gradually learning to hear. And so, here we are, 100 quiet facts about the most mysterious objects in the universe. We have traveled from the trenches of World War I, where a physicist first solved Einstein's equations, to the distant hearts of galaxies where supermassive black holes have existed for billions of years. We have visited the event horizon, that invisible threshold beyond which the cosmos keeps its deepest secrets, and stood at the edge of the Schwarzschild radius, thinking about time slowing and space bending into darkness. We have heard, in a way, the signal of two black holes merging a billion light-years away, a brief chirp of data marking an immensely energetic event. We have also seen the first image of a black hole, a glowing ring surrounding the deepest darkness ever captured. It would be easy, perhaps, to think of black holes as peripheral, extreme and exotic, but ultimately separate from the ordinary flow of cosmic life. But this would be mistaken. Black holes are not bystanders to the story of the universe. They are among its main characters. They regulate the growth of galaxies. Through the energy their jets and winds pump into the surrounding intergalactic medium, they prevent galaxies from growing unchecked, keeping the cosmic ecosystem in a kind of balance. They produce the heavy elements of the universe: gold, platinum, uranium, through the cataclysms of their formation and the mergers of the neutron stars that are their close relatives. They seed the universe with angular momentum and turbulence that helps shape the formation of stars and planetary systems. They serve as the ultimate recyclers, taking in matter of all kinds and encoding information about it in ways we are only beginning to understand. They also represent the universe's deepest commitments, A black hole is the universe's statement, written in the language of curved space-time, that information is conserved, that entropy increases, that mass and energy are equivalent, that the speed of light is the universal limit. All the fundamental principles of physics are written into the nature of black holes, more clearly and more extremely than anywhere else in the observable cosmos. To study a black hole is to study the universe at its most itself. Before we close tonight, let's rest for a moment in a few of the images that feel, to me, most worth carrying. The image of Karl Schwarzschild in a trench in the First World War, solving Einstein's equations and mailing the solution, so elegant, so complete, to Einstein himself, before dying of illness a few months later, never knowing what his work would mean. The image of the S-star S2 racing around the invisible heart of our galaxy at nearly 3% the speed of light, completing its orbit in just 16 years. A star circling a black hole that outweighs it by 1,000,000 to 1 in the same galaxy where you are lying quietly right now, listening to these words. The image of two black holes circling each other for millions of years in the heart of a distant galaxy, spiraling closer and closer until finally they touch and merge in an instant of extraordinary energy, sending out a wave through the fabric of space-time itself, a wave that traveled for over 1 billion years and arrived at our detectors as a brief, faint whisper in the data. The image of a black hole at the end of the universe, when all stars are gone and all galaxies have dissolved, sitting alone in the darkness, slowly, imperceptibly growing smaller through Hawking radiation, over timescales no human language has words for, until at last it too is gone, and the universe is left in a silence more complete than any we can imagine. These are images from the deepest parts of the cosmos, and they are also, in their way, very gentle ones. They remind us that the universe is old and patient, and has seen things we cannot imagine, and that it is not hostile or indifferent, but simply vast. Vast in a way that includes us, vast in a way that produced us. At the hearts of hundreds of billions, at the hearts of hundreds of billions of those galaxies, supermassive black holes sit in their ancient stillness, holding their secrets, bending light and time in the vast, quiet dark. You don't need to hold on to any of what you heard tonight. Let it drift. Let the facts and ideas float gently out of reach, the way thoughts do just before sleep, half remembered, peaceful, dissolving softly into the background. Let your body be heavy and still. Let your breathing be slow and easy. Breathe in gently and out, in and out. The universe is very large and very old, and it has been here long before tonight, and it will be here long after. There is nothing you need to do with it right now, nothing you need to understand or remember or decide. You can simply be here, warm, still, breathing, a small and quiet part of a vast and beautiful cosmos that takes care of its own in its own patient way. Your eyes are heavy, the darkness is soft. The space between your thoughts is growing gently wider, like the space between galaxies. Slow, quiet, expanding into peace. You are doing beautifully. Just rest. Let the words carry you a little further down into the quiet. Down and further down, into sleep. If tonight's journey brought you some peace or wonder, we'd love if you'd like this video, subscribe to the Night Science Facts channel, and leave a comment letting us know what topic you'd like to explore next. Whether that's neutron stars, the Big Bang, dark matter, or any other quiet corner of the universe. We'll be here whenever you need somewhere gentle to land. Until then, sleep well. The universe will still be there in the morning. Good night.